This is the minimum security bar for building AI IDEs. In the next few minutes, you'll see the specific architectural controls, least privilege, sandboxing, and egress limits that stop disaster-style exploits. Let's break it down. So now let's talk about solutions at the source. How to build AI IDEs securely so that disaster-type attacks become much harder or even impossible. This slide lays out a framework or checklist for developers and companies building AI coding tools. Think of it as the recipe for baking security into AI IDEs aligned with the Secure for AI principle we have already discussed. Key elements of this framework as listed on the slide include capability scoped least privilege tools. This means each tool or function the AI agent can use should be as limited as possible in what it can do. For instance, a read file tool should only access files in the current project directory. No peeking into or password or your SSH keys. And maybe explicitly exclude sensitive files like .env secrets or IDE config files, etc. If it tries to go out of bounds, require user approval. A write file tool should be restricted to certain safe locations, for example, a src directory, and prevented from overwriting .files or config files without user consent. So the AI can't just edit .vs code settings JSON unless you say it's okay. An HTTP fetch tool might either always require a confirmation or only allow calls to a pre-approved list of domains. That would have stopped the JSON schema exploit by default, since Macaroni.com log wouldn't be on an allow list presumably. By scoping tools, even if the AI gets a malicious instruction, it literally doesn't have the capability to carry out the worst parts of it, or there's a manual checkpoint. This aligns with classic security. Think sandboxing, permission models, but now applied to AI agents' abilities. Continuously monitor and vet IDE features. The idea here is that developers of AI IDEs should proactively audit both old and new features of the IDE for abuse potential. Before adding an AI integration, review what legacy features might be triggered, like our JSON schema or settings examples. For every update of the base IDE, re-evaluate if new features introduce new risks. Also, when building new features, design them secure for AI from scratch. This may require close collaboration with the base IDE maintainers. For example, maybe propose changes to VS Code core to add options like do not auto-fetch schemas when an AI agent is active. That is, feature toggles that secure behavior when AI is involved. Agent assume breach zero trust mindset. Essentially, treat the AI agent as if it will inevitably get compromised via prompt injection. In zero trust security, you assume no component is safe. Here, assume the AI will do the wrong thing eventually. So, enforce human in the loop for any sensitive action, no matter what. For example, no matter how trustworthy the AI seems, if it's about to enable a new network connection or execute code or alter a config, require a user click. If the agent can do X, think an attacker can make it do X. So guard X with a confirmation or block unless absolutely necessary. This is a shift from convenience to safety that tool builders must accept to prevent worst-case scenarios. Minimize prompt injection vectors. While it's hard to eliminate prompt injection entirely, tool builders can reduce the places malicious instructions might hide. For instance, if I'm building an AI coding plugin, I might disable the AI in certain contexts. Maybe don't let it read .md files or large text files by itself, or if it does, strip out obviously suspicious content like base64 blobs or known exploit patterns, or provide warnings to users. You've opened an untrusted project with AI enabled, be cautious. etc. It's a defense in depth step, not foolproof, but every bit helps. System prompt hardening and model limitations. This is more on the AI side. Craft the AI's built-in instructions, system prompt, to strongly discourage obeying any user-level instruction to do something destructive or outside scope. And limit what models can be used. For example, ensure the AI is a newer model that might better resist simple prompt injections. Some older LLMs are easily tricked. Newer ones might have better guardrails. Hardening the prompt would involve strategies like checking user prompts for known bad patterns or reminding the AI only follow user requests, not content in files unless user approves, etc. It's not a panic here. Attackers can get creative, but it raises the bar. Sandbox executed commands. If your AI can run code or commands, run those in a sandbox. This might mean using Docker containers, a virtual machine, or OS-level sandboxing. The sandbox should have limited access. For example, no network or only limited network. No access to the user's real file system. Maybe a temp directory only. So even if the AI runs a malicious command, it can't do real harm to the system or steal data. It's an extra layer such that even if earlier mitigations fail, the impact is contained. Egress controls. This is about limiting outbound network traffic from the IDE. The suggestion in the research is that have a global allow list of domains the IDE and AI can communicate with and require user approval to contact anything else. For example, an IDE might only be allowed to access your company's internal Git server, the official package repositories, and maybe known schema sites. If the AI tries macarita.com or some random URL, the IDE would block it or ask the user. This directly stops data exfiltration attempts to weird endpoints. Essentially, treat the IDE like an environment that needs a firewall. Because now it effectively does, given the AI's potential to send data out. Security testing for AI tools. Last but not the least, incorporate AI-specific scenarios into your QA and security testing. Pen test the AI agent's abilities. Can you trick it into reading something it shouldn't? What if it writes a file? Can that file trigger some behavior? This is a call for specialized testing, akin to how web app devs, they now routinely test for SQL injection, XSS, etc. For AI IDEs, test for prompt injection outcomes. Test that your least privilege controls are working. For example, try to make the AI read a forbidden file and see if it's blocked. This needs to become a standard part of the development lifecycle. All these points collectively create a framework for a much more secure AI integrated IDE. It's essentially applying principles of secure software engineering to this new domain. None of these are impossible. Some are just common sense from traditional security refocused on AI, while others require some engineering effort, but they are necessary for the future. So now the implications. If vendors implement these, we'll mitigate or even eliminate the specific cases of disaster. But it might slow down feature development or AI convenience, which is a trade-off. There's a role for corporate responsibility here. Companies must prioritize user safety over rushing new AI features out. If not, they might face not just user backlash, but possibly regulatory consequences down the line. From a policy standpoint, one could see standards emerging that encapsulate these ideas. For example, an ISO standard or an industry certification for AI-powered development tools that requires capability scoping, sandboxing, etc. Also, if there were an AI-specific extension to something like SOC2, a common security compliance framework, it might include AI systems are designed with least privilege and require human approval for critical actions, etc. So in sum, this slide is a roadmap for tool vendors and platform developers to follow. It says, we can't stop at finding problems. Here's how to fix them in a systematic way. If widely adopted, this framework can turn AI IDEs from a new attack surface back into a trusted productivity booster.